Okay, welcome back. You might notice some new technologies being used now to record these sessions. Got a little bit of an upgrade on a webcam and even a clip-on mic. Hopefully it's working. Also, feedback heard loud and clear. I've increased the size of the font a little bit in here, so hopefully you guys can see a little bit better. This is probably alright, but please feel free to continue to give me feedback on these lectures on the Discord and in general. Definitely want to hear from you guys what's working and what's working less. A couple of questions have come up, and I'll be doing this later this afternoon, bringing the class repository online. The class repository is going to be an effective fork of Alberto's class repository, but given that we may make changes to it and things like that, please keep your eye on that repository that I'll share. I'll be sharing it on the Discord relatively soon, so you guys will have the right link. But it should be very close to the other repository, so if you want to take a look at that, I'll provide the origin fork link as well. Great. So let's dive back into it. So last we were doing this, we effectively got as far as initializing a window with Windows. And I see some silly code here and so on, but we'll get rid of that as we go along. I'll also introduce the EHM concept, and hopefully by now you've kind of messed around with Visual Studio a little bit and have gotten somewhat far in getting a few things kind of going as well. So with that, let's now move into the initialization of OpenGL, which is what's going to allow us to actually render anything into our window. So to get started with that, we use what's called a graphics device interface, or GDI context. And this will basically give us a context into the window that we rendered. Just to kind of review, right, I'm going to run this really quickly, and you'll see that all we really get is a window that pops up and nothing's in it, right? It's completely blank, which isn't so great. And if we do anything, like if we hit that letter like we did A, nothing will show up in the output or in our console, because we just ran through this code and it went straight to the exit, which is not that great. So let's actually do something, and then eventually we get to the event loop, and by the end of this session we'll be able to have a full end-to-end application that's rendering something with OpenGL. So to start, let's add our context, which is just this handle to a device context, which we're going to initialize with null pointer. That's just good general behavior. And then we're going to get the device context from Windows by doing this. And this function, again, it's a Windows function. A lot of this stuff is Windows API stuff. And if you ever need to look up what it means, go to the MSDN and take a look. This may fail, so let's just add our little, just like a CN. We don't actually have to add a message every single time. This is kind of a simpler version of the EHM above, which if you put an M, you can pass it a message. If not, like for example, if I create a little test here, a CN, if I hit this and it'll be null, it'll go an error, and it'll give me a bunch of a reason why. Right? I guess it won't give me a reason why. I have to turn it on, but either way, it'll catch it and it'll send you to the error, which is good enough for me. So let's start for that, and then let's set up the pixel format of the device context. And so this one is a little bit of a convoluted thing, and hopefully you don't have to do this very often. Pixel format descriptor, PFD, and then we're going to set that up. And so the first thing, like most Windows structures, we're going to have to pass it its own size. This is generally just used by Windows to determine whether or not the memory you've passed the function is valid. Then we're going to use version number 1. and then we're going to provide a bit of format flags. So we're going to add the PFD draw to window, and then we're going to go PFD support OpenGL. So you can kind of see that OpenGL is actually built into the Windows operating system level. And we're going to add also the double buffer, which we'll explain what that is a little bit later. But double buffering allows you to render to one buffer while the other one's displaying, so you kind of imagine it's a bit more performant. You can do more than double buffering, but generally speaking, double buffering is where you get your maximum performance benefit. And then we're also going to use the RGBA. Notice that's the only real one that you get. There's no other ones, so it's unclear why they actually ask for that at all. And then we're going to go 16-bit color depth. This is actually important. And then we're going to ignore the color bits. Is that all the bits? Let's see. Here we go. If you ever really want to know what something is, you can right-click, go to Definition, F12. If you're using Visual Assist like I do, you can go Alt-G, which is what I do. And we're going to ignore, as you can see, we've already implemented the version, the last thing was the color depth, so we're right here. And now we're going to ignore the red bits, the red shift, the green bits, the red shift, the blue bits, and the blue shift, and then the alpha bits and the alpha shift, and the accumulation buffer and the accumulation bits. And we really just only want the depth buffer, 32-bit. So you might ask, why do we have all these numbers? But that's okay. So we're going to just do this manually. We're not. I have no patience for this. Let's do the following. Like we did in the previous example, we're going to do the following. This also saves you a bit of documentation. Of course, Hebrew. All right. And now we're just going to move all of our stuff up here. We don't need this anymore. We're going to equal to there, equal to 1. We're going to do 16. And then we're going to make this guy equal PFD type RGBA. Great. And just as again, this will mean that we don't actually have to set anything that we don't need because we've set it to 0 already. So cool, I'm not going to set any of this stuff, but I do care about the depth size, which is going to be set to 32, the reason of which will be obvious in a later lecture. And then we're also going to get rid of these. We're going to set the layer type to the main plane, which is the main drawing layer, and reserved is equal to 0. The layer masks are also ignored. So in theory, you could just delete all this stuff, but I'll leave it there because it's cool looking. And there you go. So now we're going to choose the pixel format for OpenGL. Choose pixel format for our HDC with a PFD. Actually, this is not an OpenGL function. This is still Windows, so we don't really need to use the GL uint, which you can see I already have an error there, which suggests that I don't know what I'm doing, which is true. Most of the time I don't know what I'm doing, but that's okay. For the time being, we'll pretend like I do. And now we've basically chosen the pixel format, and we just want to make sure that the pixel format is not 0. And so we're going to create a little test for that. Pixel format is not equal to 0. Again, the check Boolean is checking for the negative, so we want to put in the conditional that we expect. So we expect things to not be 0. But if it is, let's pass a fail, and then we can't find a suitable pixel format. Now, what does it mean we can't find the suitable pixel format? Basically, this function will try to create a context with the pixel format that we provide. So if we provide something with a funky doodle thing that our hardware or our OS or our display doesn't support, then we're going to get 0 and a null. Otherwise, we're going to get a pixel format that is what we expect, like a non-zero 1. And once we've got that, we can set the pixel format for our device context to the pixel format with our PFD. And again, if we fail, we want to pass that fail, and then we can say can't set the pixel format. Generally speaking, if you use these sort of off-the-shelf values and things, you'll never fail this. But it's good to know that if it does fail, and that's important to keep an eye on. So now let's create the handle to the OpenGL rendering context. So we'll call it the HGLRC, and we call it our rendering context, RC for rendering context. And here's our first actual OpenGL function, and we're going to quickly call this, and we're going to say, hey, HRC, we want our WGL create context, and we're going to pass our HDC to that function. Great. Now, this should pass back our HRC. As you can see here, the HDLRC is a handle. Ultimately, it's just a handle, like everything else that we've been using. So if this fails, we actually kind of want to know. Here we want to do CNRM, HRC. Our fail code would be result. Actually, you don't really need this fail. They're all the same fail, so it doesn't actually matter that much. Let's just save a little bit of time. And so if the HRC is null, then what happened? It means that we cannot create our OpenGL rendering context, which is a real bummer, because without a rendering context, you can imagine you can't quite render anything valuable. So that will get us going. But now this is sort of a weird kind of aspect of OpenGL, that you kind of have to create a temporary rendering context that you then set to your rendering context. And then from using that, then you can get the version of OpenGL. It's a bit of a backwards design pattern, but it happens only once and early on in the program, and so it doesn't really matter that much. It's kind of an annoyance, but it's something that we'll do relatively quickly. So let's kind of quickly go through it, and then we'll go HGLRC, temp RC, let's call it HRC, is going to equal, again, we're going to call the same thing, WGL create context, and HDC, we don't actually have to pass anything else to that. And then again, we're going to make sure that our temp HRC, actually is not null. And then we're going to call WGL make current. And we're actually going to pass that to the HDC. So our device context is now going to use our temporary rendering context as the current one. I'm going to wrap this in a CBM because I want to make sure that if it fails, then that means that we can catch that error. I can't activate the GL rendering context. Okay, cool. So, in theory now, we are good. Are we good? Let's test it out. Let's try to get down here and see what happens. And you'll see me do this int a equals 5 a lot. That's just me adding a little bit of code so that the debugger hits it and doesn't like skip. We're missing WGL create context referenced in win main. Now, if you guys have been sort of following along at home, you probably already hit this because you probably went way ahead of the lecture. So what's the issue? Why can't it find that function? Well, that's because we need to link it. We need to add the actual code to the executable so that Visual Studio knows where to find that. Now, I'm not going to pretend like I know this off the top of my head. I don't. You can see that we're not including anything at the moment. So I'm going to go to another project that already has this all figured out. And you'll notice that over here, it's including these three libraries. The glue, which is the extension library. I think we talked about that in the previous lecture. This is the OpenGL 32 library, and this is the glue library, which we're not going to use in this particular coding example, but we'll use pretty often. If you have OpenGL installed, generally you will with Windows, like you don't really have to install this like you would with DirectX and other libraries. You should be able to just add these to your project. To do that, you go to Properties, you go to Input, Edit, just like that. In fact, if you want to get fancy, you don't even have to do it here. You can do it by way of a preprocessor macro, which I always forget. This is something I always forget, but great. Here we go. That's really it right there. So you can go even into your main, and let's link our libs, and here's the code. This is not necessarily portable. It's not going to work everywhere, but it will work in Windows and it will work in Visual Studio. So generally speaking, you really don't want to be using if you're working on a big project, you don't want to be using Visual Studio to set up your project and your configuration. You really want to be using something like CMake, Meson, Makefiles, but those are quite heavy. You're going to spend a lot of time setting up the configuration, and it's nice when you have one huge project, right? Like if you're running your own engine or your own game or an application with C++ and so on. But if you're running a little quick project or whatever, you can do it this way. You can do it in the project settings of Visual Studio. You can use the solution. There's really no shame in doing it the way that is easiest for you. And so now, in theory, first I'll build a hit F7, but still, there's a missing something, there's an error. And so it cannot find my glue 32 libs. So by adding this file, it failed. Or I'm sorry, this one. So for the time being, let's comment it out, and I'll tell you the reason most likely, because there's probably a different linker setting for here, the files in a different place, and so on. I'm not going to find that because you'll notice if I open this one, there are no errors. So there's something configuration thing that's about mine that's not the same as the other project. But for the time being, let's just ignore glue because we're not going to use it. Great, and now we've built successfully. And so now if I hit F5, I'll get that far. We have no errors. We're happy. So we're pretty good in the hood so far. So great. Let's kill that breakpoint. All right, so now we're going to try to extract from OpenGL what version we are. So we're going to get the major, version major, and we're going to start off with what we know to be the minimum version, which is 3.1. And then we're going to define some attributes that we want. So first we're going to go context major version ARB and major, and then WL context minor, version minor, and finally we're going to context flags ARB, original context forward compatible with ARB, and because we want our GL context to be forward compatible, and these attributes are going to be passed in. Why can't we find this? Obviously, www.h, it's there, but we can't. It's going to give us a bunch of angry noises. Well, notice that there's a couple of issues with this, right? These functions, we're not going to find them because we have not included our OpenGL code at all. So we need to include our headers for OpenGL. Let's do that. And to do that, let's go into main.h, and we're going to include, first off, include that specific set of missing capabilities. We're going to include the glue.h. You'll notice that this file is in the repository already. And so then we're going to, include GL. What else do we need? We probably need the W glue, which was what we were using in that specifically. And I guess that's it for now until we get yelled at again. So let's see if this fixes the issue, and then great. So now we're able to compile that code properly. And so now let's get this going. So if glue is supported, first off, we need to maybe fix that, and then we want to make sure that we have this code in the right place. Looks like it. Now we might get yelled at because I'm pretty sure this is a glue function and we couldn't find glue library, so we might have to fix that. But let's see if this works. So we're going to check if the extensions that we need for the version number that we want, we're requesting 3.1, is going to be supported. And so we're going to say HRC is equal to WGL create context attribs ARB HBC null. We don't use that, and then we're going to pass in our attributes list. And what this does is it requests a context with the given attributes that we've requested. And first we will make current null pointer. This basically resets the context. Then we're going to delete the context, which was the previous temporary one, and then we're going to make our current context the HBC and our current HRC. So you can kind of see that here, if we're able to create a context, then we will go and try to create a context, We should also CN this, because if this fails, we don't want to do any of the above below. We just want to quit. Right? And then we'll try to, where we disconnect our context, we delete the previous one, and then we set the new one as the context. Great. So now we need to initialize glue, which I think is where we're going to get into a bit of trouble. But let's see how well we do up until now. One failed. So 2 resolved. And again, just like I expected, our glue is supported. The function that we were calling here is not found. And so we do need to link this library, glue32s.lib. Unfortunately, when we try to build it, it will fail. And so now you have to understand, so usually this is what I do. I don't really memorize most of this stuff. I'll have a project that already has things sort of figured out, and then I'll kind of, A and B. So this one is linking directly from where you'd expect. Sometimes you'll have an additional include folder, or include linker folder, and so we can search for that. There's nothing there. So you can see we have an additional include folder, but we don't have additional linker folders. Okay. So we're missing this glue32s.lib. So let's take a look at our file structure, which is probably where we're going to find it. And let me quickly go to the location of this project on my glorious Dropbox. All right, so let's see here. And here we are. And so let's search this for libraries. Great. And you can see that the glue32s is here. So let's open that, open the file location. We can see that it's in include GL lib. So why isn't it finding that particular thing? Well, we could kind of trick it, right? And we can say, okay, well, our project is, let's see. Clearly, this is somewhere where we don't want it to be. Or, let's see if it's in the post. Right here. Post build event. And then it copies all of those binaries. Oh, I see. That's not really of any interesting thing for us. All right. Well, we're gonna cheat just a little bit, and we're going to simply well, for whatever reason, we've got the binary, the glue is in there. I see. We can kind of cheat here a little bit. And what we'll do is we're going to put that here, which is a bit of a hack for the time being, and it still won't work. Great. So let's remove this. And what we can do is actually explicitly tell it where to find that file here. And sometimes if you forget the macros, Oops. Here. So what we want is we want our project dir, then out a couple, because our project directory is here, then we'll be here, then we want to be and include gl lib. Right? And then we're going to include this file. Okay. Apply, okay, get rid of this. All right. And let's try to build it. Cannot find file because I did that incorrectly. Okay, project dir. Let's just try this. So that was working. Maybe the pragma is just not being happy. No, cannot find that file. All right, well, I don't want to drag this too long. This is, by the way, what 90% of development looks like for anyone interested, but there we go. Let's just cheat and add the entire absolute path and 2 unresolved externals. And why is that? What's missing? We had it, but maybe we need the other one as well. Let's see. Great. So now we have all the code linked and correct, and we can run it. The code extension cannot because glue 32 DLL was not found. Right. So you'll notice that in here we also have glue 32, and this needs to be copied into the correct place so that the binary can find it. In this original project, you can do this with the copying all of this to the binary, which is fine. Alternatively, when you're kind of in a bind like this, you can simply go into your project, and we're in debug, and wherever your executable is sitting, which is apparently here, you can just throw it in there. And this won't get deleted unless you clean it. In the future, what you really want to do is you want to just make sure you copy things around the right way, so you get to, you make sure that on a run it's the same. We'll talk about that more later maybe. And now it'll find it and everything's fine. Great. Cool. I'll generalize this in future projects and also in the repository when it's up. So don't, if you don't understand how to like bypass these issues, we'll talk about it in the future. Keep in mind that if you do an absolute path setting for any of these required files like the DLL for glue or even the binaries, like the library binaries, it may not compile or run on somebody else's computer. So you do want to resolve those issues before, say, you deploy this to somebody else that might be using it for whatever reason. Great. So let's start off and implement glue. So glue glue experimental this is not something I'm a huge personal fan of, but glue defines effectively a Boolean global. This is bad design, but Still, we can use it for the time being. We can set that to true. And now we want to initialize, and we're going to initialize this inside of a CB call, glue init. We want to make sure that this is that this returns glue OK, and if not, then we can say failed to initialize glue. So glue, all it's doing is making sure that all the extensions that you have, that you're employing within the context of the version number of OpenGL are available to you to use. Some functions in OpenGL are not available across all OpenGL versions, and things that are not in a core version or like backwards compatible or part of the core OpenGL specification per the ARB are extensions. And so you need to use something like glue, or you need to do this manually and manage your extensions manually. It's up to you. Glue is probably better because it's pretty good, and generally speaking, it doesn't do anything particularly intelligent. It's just going down a list of functions and just sort of copying them over into your function space. And so it's not the cleanest code, but I mean, I've implemented my own exception handler, extension handler instead of using glue. And we're talking about thousands of lines of code that are really, really lame and boring. And every time you hit something you need that you don't have in there, you have to write like a lot of code and know that that's the issue. Cool. So the last thing we're going to do here is we're going to set the GL clear color to something. We're actually not going to use this yet. But cool, and that's really the end of our OpenGL initialization. So let's see what we get here. If we run this, nothing, right? Even though we set that to a weird color, and it doesn't actually do anything yet. And we'll talk about why in the next section. Great. So now let's implement our first ever shaders, which is pretty cool. So what we're going to do is we're going to write the shaders inline, which is not something you should ever do. GL char, cannot be located. Why can't it be located? Well, maybe it's because we have not included OpenGL. So we probably want to include gl.h, which will finally give us a lot of these uints and stuff like that. So great. We're going to create GL char, and we're going to call, well, this is going to be a PSZ vertex shader. You may be wondering what PSZ stands for, and that is a pointer to a null terminated string. It's a very annoying thing to remember, but it works. GLSL, and this is going to create our inline shader. And so first we define the version to be 330, which is 3.3, although we're using 1 up here, but that's all right. Let's stick to that. And then we're going to define an input of type vector3, which is the vertex position. Great. Now we're going to define a little main function. Now the vertex shader, as we were talking about in previous lectures, is really just a program. And some of these variables that you're seeing, like GL position, those are actually variables that are built into this shader stage. So the vertex shader expects, a certain amount of inputs, but generally you define what those are, like a vertex position and stuff like that. But it can pass on a couple of different things to the next stage, such as the position, or even a few other kind of inbuilt GLSL variables. But for the most part, position is the main output of the vertex stage. So what we're going to do is we're going to just take the position, the point position, and just append a 1 and turn it into a vertex of 4. And you'll notice that we talked about this before with regards to alignment. And the GL position is a 4-component vector. So if you have already passed in a vector of size 4, this line of code goes away, right? You would then just pass in a vector 3, a vector 4 to that GL position. You don't have to create an additional item in between. And in that sense, it's a little bit more efficient. And so this really shows how the alignment piece does, even in the context of a shader, really help. Now let's make the pixel shader, which is the next bit. Great. And then we're going to go version 3.3.0, and then we're going to go vertex for output fragment. So you can notice that we don't actually need to define an input for this, because the GL position is the output of the vertex shader, but the input of the pixel shader. You can define different inputs and outputs for shaders, shader applications, and so there's a lot of different ways to handle this. And later we'll get into uniform blocks and things like that as well. But for the time being, you can kind of think of this as okay, it's getting an input in the form of a position, and then I'm going to output it in the form of a color. And that's exactly what the pixel shader stage does, is it simply outputs a color. And so fragment is equal to vertex 4, 1.0f, 1.0f, 0.0f, or actually we want 1.0f here. And so this will give us a red output with 100% opacity, which won't mean anything for a little bit of time. Great. Awesome. So we've written these out. Usually an engine will, you actually have a program that loads these things from disk, and you wouldn't have them inbuilt this way. But all the OpenGL compiler for shaders expects is a string. And so you can do this in the code. It doesn't really make too much of a difference however you do it. So great. So GL. Now let's actually compile the shader. So we're gonna do that, and you'll find this pattern pretty common in OpenGL, where you do some stuff on the GPU memory-wise, and it gives you back an ID, like a handle. It's not a memory location; it's a handle specific to that type of object. But for all purposes, it's kind of like a pointer. When you pass that to OpenGL, it'll give you the appropriate thing. So GL create shader is a function from OpenGL. You'll notice though that it's in glue. So this is one of the extensions. The traditional legacy OpenGL did not have a programmable pipeline, and so this is one of the extensions that glue gives you. So if you don't include glue and just are using OpenGL off the shelf, you will not be able to do this. Great. And it's funny, right? Like, this will actually create the shader for you, and if you want, you can actually do a CNM here, even though it's not a pointer type, because it's going to be checking for null. If you get passed back a 0, you cannot create vertex shader, right? Let's just try that out, and you'll notice that after I create it, when I go to the next, vertex shader is equal to 1. So that's our first vertex shader, and it won't fail because it's not 0. This is unnecessary for the most part, but you might sometimes want to double check. And so now, it's simply, all you have to do is you pass the source code to that ID. We're creating one shader program, and then we're going to pass in the PSZ vertex shader, and then finally a null. Not null pointer, it's a long story, but great. Yeah, OpenGL, generally speaking, you can't always use null pointer in the way that I would like. And then compile the shader, the vertex shader ID. This is, again, a very, like, think about it this way. The verbosity of OpenGL may be kind of annoying, but what's happening is we're creating a shader object on the GPU, then we're loading the source code to the sort of slot that's associated with that object, and then we're compiling it, right? It's kind of like, you know, here we go, this is what we're looking for. It's not, these functions do not return anything. And so the reason this process takes place this way is this is effectively manipulating a piece of hardware in your computer that isn't that smart, right? It only is a very mechanical thing, so you have to really lead it along. So we're going to do the same thing with the fragment shader, or the pixel shader. And all I'm doing really is going to change I'll go to fragment just because that's the word. And I called it pixel up there, but if we want to be consistent. Great. And this should now link or compile the fragment shader as well. Now we need to combine the two of these into sort of a program, because you can't have like a pixel shader and a vertex shader on their own. They have to connect to each other. And so now we have to create a program. The program is a combination. It's almost like a memory space context, right? And you can have lots of different programs. You can switch between them. OpenGL is quite flexible in that way. So to create one, again, we have this program ID. And then we just GL create program. And you'll notice, again, this function is in the glue. So this is not something you get right off the shelf with OpenGL. Now we attach the shader to the shader program ID. We'll attach the vertex shader ID, and then we'll attach the fragment shader ID. And cool. Now we have to just link the program. And this is sort of where we really want to start to check if anything went wrong. So first we want to go glint. You'll notice all of these GL types are sort of like the same as normal types, but just slightly different. They just ensure that what you're doing is compatible with the OpenGL API. So if your architecture for your computer is slightly different, that won't like blow up or have a compilation error or something like that. So now we're going to request the link status from the program, and we're going to pass it into results. And again, we're going to try to get the length into log. So what we're trying to do is we want to make sure that there was no error and there's no issue in linking or in compilation. And so this next bit is simply going to kind of interface with OpenGL and make sure that nothing went wrong. And so we ask for the link status. There are other things we can ask for, like the compile status, and so we can try to see, oh, did the compilation fail? And we can do this in a kind of a generalized function, which we will do in the future, so that we can test it at every stage. Because really, we don't want to just know if the linking failed. If the compilation failed, then the linking obviously will fail. But let's just kind of do it at this level for the time being. So if the log is greater than 0, meaning if the length of the log, and I should actually change that. So log n, that's my personal kind of convention for the length, indicating the length of something. Is the dash of the underscore n at the end means it's a count of some kind. Cool, let's create a vector of characters. Program error message. And it's going to complain to me because I have not included vector cool. And now we're going to get program info log of the shader program ID with the log n, which as you can see is the buffer size, and then we're going to pass it the program 0. Now, if we just do this, and it's gonna really not be happy because the expression must be a pointer to a complete object type. We are a complete object type, but this should not. Oh, I see. We're missing one in between. So there we go. Nice. So if we don't add this bit, this is going to be empty and will probably blow up in our face. So we don't want to do that. We do want to provide this. So if we don't, it's going to give me an error because it's not a complete type. Although, it shouldn't really do that. There we go. If we do this, it'll probably crash. Generally speaking, I like to do mallocs with this stuff, but let's do it this way. Let's call as the constructor. So, CVM, false. So this will always hit it, and we're just going to pass back the program message. And you'll notice that I haven't used this in a CVM before. CVMs have variadic, I don't know how to pronounce it, but it can take a variable number of variables at the end. Variadic. Let's see. Variadic. Cool. So you can pass a variety of things to a CVM if you would like. Otherwise, if this didn't hit it, then we can debug line out shaders compiled and linked. Awesome. So let's see what happens here really quickly. So let's set a breakpoint and run through it. Cool. So cool, and compile. Great. Now we're going to create a program, links, and we're going to see if the result is bad. The result is 1. So we're looking pretty good there. And the log is going to be 0 because there is no error, and so we should successfully compiled our program. Now what we're going to do is we're going to GL use program, and that's just going to be our shader ID, and then we're going to delete the shader vertex shader ID and frame. And that's just nice to do, but it's optional because it's not a really big deal to leave that stuff on there. So now if we run this, we'll hit that breakpoint. But for the most part, we're just going to get what we had before, which is, let me build this. We're just going to get this window that doesn't really do anything, which is not very useful. So what we can do now is create something to actually upload into the GPU. And this is actually going to be relatively easy to do. So we're going to create a VAO, which we'll talk a lot more about very soon. And then we're going to create a vertex array. We're going to create one vertex array, and we're going to assign it to the VAO. And then we're going to bind the vertex array. And nice. And now we're going to create a couple of positions. And this is just going to be a little triangle that we're going to draw on the screen. You'll notice that we're already passing specific values into the GPU. But this might not look like a 3D value to you, right? This last value is 0. And so what's this all about? And so we've got -1, -1, 1, -1, 0, 1. So this is y, obviously. And so these two seem to be at the bottom. And this one's at 0. And so you kind of have to understand that on the outside, on the other side of the vertex buffer, vertex shader, OpenGL is expecting points in this sort of -1 to 1, both in the x and the y axis. And that's what these values are going to go into, because if you look at our shader code is simply passing these values directly into the pixel shader without any kind of manipulation or transformation, which we'll do very quickly in the next sections. And so, cool, now we've got our data, and we have to create a VBO, vertex buffer object. And just like before, we're going to generate a buffer. I'm going to create only one buffer. I wish they had just like gen buffer, but whatever. And then we're going to bind that buffer to OpenGL. And this is sort of like thinking like, okay, we've got this stuff and we're going to bind, meaning tell the GPU to apply the next set of instructions to that particular point. And so we're going to now take that data that we created and we're going to send it into that buffer. So we're going to go size of positions. So this is the amount of data we're about to send it. And then we're going to send it the memory location. This is the CPU memory location. And the usage is sort of a temperamental thing, but it kind of tells the GPU a little bit about how we're going to use this data. So the GPU may want to put this memory in a different place depending on whether we're going to change it every frame or not. But static draw means we're not going to change it. We're going to just draw it as it is over and over and over again. And so now we've taken that position data and we've pushed it up into the GPU. So it's not sitting in a memory location in the GPU. Next, we need to create a buffer ID that we can then use. So we can basically sort of send this data to the right place in our shader. And this is, I'm not a fan of this naming so much, but basically the idea is you can kind of see here we have a point position, and we're binding the attribute location in the shader to our thing. So actually let me do this. Let's call this the position attribute ID, and then we're going to call it point position. And this is what it's going to look for. And if it doesn't exist, you're going to get an error. And so this is the part where you're actually linking your C++ program to your GPU program. This is a really critical point. And a lot of times, if you're having issues getting your stuff to run or data to flow through, this is where that problem is happening. And so now we're going to enable that that particular attribute on the vertex shader, and then vertex attribute pointer 0, 3, GL flows, GL false, we're not normalizing it, we have a 0 stride, and GL void 0. Cool. This sort of tells it what to expect. So we're passing it a, let's look at this definition a little bit. It expects an index, which is usually going to be 0, a size, so how many variables, what's the size of each of the elements that we're passing it. Is it normalized, which means it will normalize it on the GPU side for you, which you usually should not do. And then stride, which is sort of what's the how, like, in what way should it look at the data. So if you're sending it kind of lumpy data as a variable size, you can tell it like, okay, this is how I want you to go through it. And then the pointer, which usually is used in different situations, such as when you're passing into an offset of a data set, or you're doing this kind of runtime per frame. So a bit more advanced stuff that we're probably not going to touch in this course. And cool, now you've got the data in there. So let's just run through it really quick, but we won't be able to see anything yet because it's not rendering anything. Cool, so we've generated the buffers, the VAO, the VBO, and we're good. We still don't see anything. You might ask yourself, like, why do we do the VAO at all? Like, what's the point of the VAO? And that's because all of this sort of exists inside of the context of that. So we're in the vertex array, the VAO vertex array, and then inside of the vertex array we create a buffer array and connect that to the vertex attributes of the shader. So if you were to create another triangle, you would have to repeat all of these stages as well, unless you were creating additional geometry or an additional buffer inside of the VAO. So generally speaking, one VAO per VBO, but you can mess around with it more, and you always have to apply the vertex sort of descriptor, which is what's being done here in the bottom. Great. So now we're not really getting anything done. We run through this, and it immediately pops out, and it's done, and the application is over. So what we want to do is we want to create some kind of loop. And so let's first off say, line out here, starting game loop. And then we create this message. And the message is actually from Windows. It's a Windows message. And for no other reason, we set it to kind of the null, into a 0 set for the time being. And now, while message.message is not equal to wunquit, which would mean that Windows has told us to quit, we do this thing called peak message, which we then apply that to our message with null 00 PM remove, which means we're removing that message from the message queue. And so if we received a message, if there is a message in the message queue and we peak it, so this is a non-blocking, it's just going to keep on hitting it, it's not going to hold on and wait to do that, then we're going to translate the message, which just makes it, converts it into a format that we can use, and then dispatch the message, which will actually dispatch it to our own Windows process, which we defined above in the last time we did this. Alternatively, if there is no message, then we just render. The truth is you don't have to else this, but whatever, we'll go simple for now. And to render, it's actually really simple. We go clear, GL color, buffer bit, and then swap buffers, HDC. Remember when we set up a double buffer situation? This is what's happening. So we're rendering to one buffer while this one is being displayed. And then when we're done rendering this, we swap it. So then now we're rendering to the other one. And that way we don't have to wait for the rendering to be complete before we can present an image. And we don't have to stop presenting that image while we're accessing its memory location. So this is actually already enough, and we'll be able to see a gray screen. And that gray screen is because we set the clear bit to gray. And now, if you remember in the Windows process last time, I said if I hit the letter A, it's going to go A. So you can kind of hopefully not see that, apparently. Great. Well, not clear why that's not being handled, but anyways, we'll deal with that in just a minute. Great. So you notice there's no triangle there. Obviously, what's the deal with that? Well, we want a triangle there. So how do we do that? Well, we go and we call this function called draw arrays. We're going to draw a set of triangles. That's the type of primitive we're going to draw, and we're going to set that this is like the offset is going to be 0, and the count is 3. Now, this is a bit of kind of a simplification, because up above here we bound the VAO that we're going to render, right? But so if we don't do that, then this is going to fail. But because we've already done that, it'll work. So sometimes my recommendation is you want to do that and then null. And this is just to prove to us that we're rendering the right triangle over and over and over again. And there's your triangle. It's a nice red triangle. Cool. Now, it's not clear why we're not getting this key down thing, but it just looks like we are not properly converting the value. Let's do this. It's never clear to me why it ever does that, but it's cool. So let's do that. The value, oops. The value that we're getting is 87, which is 97. Oh, maybe I was just hitting the wrong button. $83, $93. Oh, perhaps I just was using the wrong button. This is the problem with having a keyboard with no labels on it. But let's see here. So, no, it's still not working. Okay. 65, 97. Well, we can cheat, at least for the time being. Anyways, now at this point, you've got a pretty good thing. You can see now when I hit the key down, it's going to do that for me. Great. So yeah, now this is pretty much it. You're displaying a window. you're opening up a OpenGL context. You are changing it to the proper version that you want. You're compiling a shader, and you're linking the two vertex and pixel shaders together, and then you're rendering geometry. And the truth is, this is it for the most part, right? Everything else that we do from this point on is encapsulating all of this functionality so that so it doesn't look like this and turns into 300 lines of code every time we want to do anything. So for the most part, I hope that this was helpful. And from this point on, we'll probably start to use frameworks and other things to avoid the need to do this level of work. But for the most part, custom engines and real graphics applications do work at this level. And while you don't really need to memorize or know most of these functions at a point where you should just be able to write them off the top of your head, you should understand what they're doing to a large degree. So that way, when you come across something like, oh, how do I do X, Y, and Z? How do I get a texture? How do I do this and whatever? You'll be able to at least Google it and figure out what's that function that you need and what's that missing piece of functionality. But don't feel this need or pressure to actually know this stuff off the top of your head. There's no way I know it. I obviously have a resource here I'm referring to, and so but to understand how it's working under the covers and to understand what each of the functions does and why it's able to do it the way that it's doing it is very, very important. So yeah, that's it for and completes this sort of initial coding example. See you next time.